Hello everyone, my name is Anirban Sinha. I am a PhD student in the Department of Mechanical Engineering at Stony Brook University. I'll be presenting the work Robust Relative Hand Placement for Bimanual Tasks. This work is done in collaboration with Nilanjan Chakraborty. The motivation behind this work is to answer the following question. How can a dual arm redundant robot choose one inverse kinematic solution pair over the other inverse kinematic solution pairs so that the chosen inverse kinematic solution pair is least susceptible to the random actuation errors. A good related work in this context is the work by Wang et al., where the authors showed a method of how joint space errors can be propagated to the task space for a single arm. On the other hand, our previous work showed how task space error sets can be utilized to choose an inverse kinematic solution that will be robust to the joint space errors. Our current work is a natural extension of our previous work in the context of bimanual tasks with actuation uncertainties in both the arms. Now, we formally pose the robust IK pair problem, which is the main focus of this paper. We define the robust IK pair problem as, in the presence of actuation error given joint space error bound and the desired poses of the left and right end effectors, we want to find the inverse kinematics pair theta star, which consists of left inverse kinematic solution theta left and right inverse kinematic solution theta right, such that the error in relative pose between the left end effector and right end effector is less than epsilon with high probability irrespective of the realization of the actuation error, where epsilon is a user defined parameter. The key contributions of the paper are: firstly, we show how to treat the dual arm kinematics as a pseudo single arm and then propagate the joint space error through the linearized kinematics of the pseudo single arm. Secondly, utilizing the propagated error sets to the task space and modifying robust IK algorithm proposed in our previous work, we developed the method of computing robust IK pair for dual arm robots. Thirdly, since relative Jacobian plays an important role in developing the robust IK pair method, we derived relative Jacobian from the relative pose between the left and right end effectors expressed as product of exponentials. The robust IK pair method that we have developed here relies on two key facts. Firstly, redundant manipulators has infinitely many IK solutions for the same end effector poses. And secondly, mapping of error sets from joint space to the task space is different for different inverse kinematic solutions. The figure on the left shows the schematic diagram of a dual arm robot whose left arm has n degrees of freedom and right arm has m degrees of freedom. The relative pose between its end effector is G relative, which can be obtained by knowing GL and GR, the poses of the left and right end effectors respectively. In the presence of actuation uncertainties though, G relative plays the critical role to dictate the success of relative hand placement and not the GL and GR independently. Knowing G relative, we can compute relative Jacobian JREL by partial differentiation of G relative with respect to joint angle vector theta. Computing J relative allows us to propagate the joint space error set to the position and orientation task spaces. Now that we know the relative Jacobian matrix of the pseudo single arm, in order to get the task space error sets, we need to first model the joint space error. Assuming that the actuation errors of the each joint follows a Gaussian distribution and no two joint errors are correlated, the error vector delta theta becomes m plus n dimensional Gaussian with zero mean vector and diagonal covariance matrix sigma. Then the joint space error set becomes m plus n dimensional ball as shown in the left figure. In order to obtain the task space error, we propagate the joint space error to the task space using J relative. By doing so, we obtain the position error set as an ellipsoid in R3 and rotation error set as an ellipsoid in the tangent space of the unit quaternion sphere. In here, we present the optimization problem that we have derived for robust IK pair problem. We came up with a min-max type optimization problem for dual arm robots with actuation uncertainties in both the arms. A similar type of optimization problem was derived for single arm robot in our previous work. The objective is the task dependent error measure M, and there are 4 constraint equations. The first constraint ensures that the computed IK pair vector theta, which is an element of Rm plus n, indeed produces the relative end effector pose as G relative. The second and fourth constraints are the error ellipsoid constraints. The third constraint is the rotation quaternion constraint. Notice that the quadratic equality constraint makes the optimization problem non-convex. Non-convex optimization problems are hard to solve in general. However, in our previous work, we have shown how this particular type of optimization problem can be decomposed into 2 subproblems, and each of those subproblems can be solved as eigenvalue finding problem. The output of the optimization problem is the robust IK pair vector theta. In order to evaluate the effectiveness of robust IK pair method, a simulated Baxter robot is tasked to perform peg-in-hole assembly with robust IK pair and with a randomly picked IK pair respectively. Here we have shown the 2 instances of the peg-in-hole task with and without executing robust IK pair. The peg and hole objects are represented as red and blue blocks respectively. The bottom left figure shows that after the pegs approaching toward the hole is completed, entire peg's cross-section lied inside the hole cross-section, and hence the task is successful. However, for the same task, when is done with randomly picked IK pair, it was unsuccessful, since peg's cross-section overlapped with the hole's cross-section, as can be seen in the bottom right figure. This is the video of the simulation of the 2 instances of peg-in-hole task execution with robust IK pair and randomly picked IK pair respectively. The figure on the left shows the success rates in performing the assembly task with a robust IK pair as compared to the randomly picked IK pair, with varying clearance value between peg and hole and the standard deviation of the joint space error sigma. The blue and red plots are corresponding to the robust IK pair and random IK pair respectively. As can be seen, when clearance is large and sigma is small, the difference between the success rates of the 2 IK pairs are small. However, if clearance becomes smaller and sigma becomes larger, robust IK pair gives more success rates than the randomly picked IK pair. The figure on the right can be used for feasibility analysis. For example, if a robot knows its sigma value for the joint space error as 0.003 radian and the allowable task space error is 0.007 meter, then that can be ensured more reliably executing robust IK pair as compared to the randomly picked IK pair. In conclusion, we have first derived the robust IK pair problem as a min-max type optimization problem. Then we showed that executing robust IK pair for tight tolerance assembly tasks gives more success rates. We have also derived the relative Jacobian from the product of exponential representation of the relative hand poses. Thank you for your time.